We have learned how to expand a multinomial raised to an n integer exponent, just like this one here. We have x plus y plus z. Their sum would be raised to an n exponent equal to 13. In the previous video, we're able to expand when n is equal to 4, and we were able to, we expected, or we were able to solve 15 terms, because the number of terms for a specific expansion of a multinomial is indicated by this formula, n plus m minus 1 taken n. Okay, where m is the number of terms. In this case, you have here 3. So for this video, if we will be expanding this, we will be expecting a lot. You will have here 13 plus 3 minus 1 taken 13, which is actually equal to 16 minus 1, that's 15, taken 13 number of elements. If you are going to use your calculators, you may use your calculators there to verify the number of terms. We are expecting 105 terms. So it would really take us a lot of time. That is why, for this video and the remaining videos after this, we're just going to solve for the numerical coefficient of our term with this little coefficient for the expansion. Now, we can solve this using a formula for the expansion, because the formula for the expansion, x sub 1 plus x sub 2 plus until x sub m, we don't know how many are they, raised to the power of n, is given by this formula. The summation of the combination of n and n sub 1, n sub 2 until n sub m times x sub 1, your first term, raised to the power of n sub 1, x sub 2, your second term, raised to the power of n sub 2, and then your mth term raised to the power of n sub m. Okay? So we're going to, when we expand, we will get here 105 elements using this. But for numerical coefficient alone, we are going to use only this portion. We will not be subjecting it to the summation. Okay? So that would mean here, we can attack this by automatically solving for this intended process. The item here known is actually our n and our m. But we don't know the n sub 1s until n sub m, or in this case, n sub 3. How do we determine what would be n sub 1, n sub 2, and n sub 3? Here comes the process. We are trying to identify the numerical coefficient for x to the power of 8, y squared, z cubed, where your x is your first term here, your y is your second term, and z is your third term here. Sorry, this is, yeah, that's a 3. We would know that this is really part of the expansion, because when you add the exponents, 8 plus 2 plus 3, 13 matches our n, right? So how would this be helpful in identifying the numerical coefficient of the term? Now, look into this portion here. That part of the expansion talks about the product of your first term raised to the power of n sub 1, your second term raised to the power of n sub 2, and then your mth term raised to the power of n sub m. With this now, connected to this idea that this is the little coefficient of the item we are trying to solve for its numerical, we would know that from here alone, here and here, we can solve for the values of n sub 1, n sub 2, and n sub 3, because we only have 3 elements here. Our x to the power of 8, the first term, so n sub 1 is equal to 8. For y squared, that's our n sub 2, and then for n sub 3, that's for your z, that's actually your 3. Now, we were able to identify this, then we can now solve for the numerical coefficient. Surprisingly for this item, since the terms x, y, and z for the trinomial to be raised to the power of 13 are having numerical coefficients 1, 1, and 1, so it's easy for us to solve for the numerical coefficient only subjecting this formula. But if this will have different numerical coefficient, let's say 2, and you have here minus, and you have here 3, we will be subjecting all of them in the exponents, but there will be a different item for that. So please stay tuned for the next video. Just for this video, we can just automatically invoke the formula of n, taken n sub 1, n sub 2 until n sub 3, because you only have m equal to 3, where this is equal to the combination for 13. Then you have here 8, 2, and 3. What is this equivalent to? This is actually equivalent to the notation of your n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. We only have until n sub 3 because we only have 3 terms. But if this has mth term, so you will have here n sub m factorial. Okay? So just bear in mind with that possibility. Hence, let me use another color here to continue at the bottom and solving for the coefficient of the term with this little coefficient. So you will have here 13 factorial over, you will have here 8 factorial, 2 factorial, and then 3 factorial. And simply use your calculators for that, you would get the result for the numerical coefficient. As mentioned, this is the numerical coefficient of the term x to the power of 8 y squared z cube. By the way, this is not necessarily to be part of the solution, but I'm just writing it here so that we will be guided on what is actually the term we're trying to prove. At the same time, you would know that these are all correct if these values coincide. So you can try this in your calculator. 13 factorial. Let's have here 13 factorial. I'm using my calculators. You could use also yours. So it's very large. You'll have here 6,227,020,800 over the product of these factorials. You have 8 factorial. That's actually 40,320. 2 factorial is 2, and 3 factorial is actually 6. So you can simply try to multiply the denominator and then simplify it later. Again, you can input this as one in your calculator. I'm just showing you the actual process so that if you have problems with your calculators to resolve to the final answer, you can always try doing this manually. You have here 483,800, sorry, that 840. So for our denominator, and our numerator is still 6,227,000 million rather 20,800. So you will have again 6,227,020,800 to be divided by 483,840. This results to 12,870. The numerical coefficient of x to the power of 8 y squared z cube. Again, not necessarily here because this is what we're looking for, but we're just placing this for the verification of the actual term. This is how we identify the numerical coefficient of the multinomial expansion for this given trinomial. As mentioned, if the numerical coefficients for x, y, and z are different, so we will be having a different, not necessarily different method, same method, but we'll be including the exponents for such. We'll have that on separate video. Hopefully this is clear for this given example. We are not expanding the multinomial, but we're just automatically getting the numerical coefficient, because if we do so, we have 105 very many terms to write. Thank you very much for watching.